Hi everyone, it's Mr. Glover here. So for today, we're kind of shift gears a little bit. Right after we develop the log laws, we're not going to use them for a day. And what we're going to be doing is focusing on the logarithmic function. We're going to talk about how to change the base of a log, as well as how to transform the log function. So let's get started here. So calculating the value of a logarithm is easy if the argument is a power of the base. So if we can rewrite what's inside the argument of the log as a power of our base, we can simply cancel the base out. So for example, 64 is 2 to the 6. So we could write this as log base 2 of 2 to the 6. We can then cancel out the 2's, and we'd simply be left with 6. So doing this algebraically is not so bad if we can write our argument as a power of the base. But what if we can't? We could use our calculators to check for an approximate value. For example, log of 5, I guess we would do log base 10. So log of 5 is 0.699. 2 times log of 2 would be 0.602. But we don't really have great ways of doing this if we don't actually have a base 10 logarithm. We don't have a button on our calculator to do, well, actually, some of you might have a button on your calculator to change your base. Most people don't. Most people are stuck with log base 10, and that's it. So how can we use our calculators to find the value of the log in this situation? So let's see if we can figure out a rule here. We're going to start with log base 2 of 6, and we're going to see what we can do to rearrange it, okay? So log base 2 of 6, we're going to define it as x. So we're going to say let log base 2 of 6 equal x, okay? And then I'm going to go straight into exponential form. So 2 to the power x must equal 6. And now I'm going to take the logarithm of both sides, but I get to take any log of both sides. I can do log base 10, log base 5, log base 2. I'm going to go log base 10, and that's because I can do it on my calculator. All right, I'm not going to write the 10, but if there's nothing there, you can assume it's log base 10. All right, so now we can use the power rule. We can pull x out, so log of 6 equals x log of 2. And lo and behold, log of 6 over log of 2 equals x. And so we have kind of gone and indirectly shown that there is a way to convert the bases of logarithms. We've gone and converted a log base 2 over to a log base 6. And so you might notice a pattern here. You might notice that the 6 was the original logarithm and the 2 was the base of the original logarithm. That pattern is going to hold true for any type of log. So in general, we can take this rule, we can extend it. Log base b of x is log base a of x over log base a of b. So in other words, if you take the log of the old base and divide it by a log of, or sorry, take the log of the old argument and divide it by the log of the old base, you now have a new converted log. A again is going to be the new base, and b is going to be the old base. And so it seems kind of confusing, but trust me, once you've done this a couple of times, you'll see that it's actually fairly straightforward. So if I want to convert log base 6 of 100 to a log that I can do in my calculator, I can simply write it as log of 100 divided by log of 6. The 6 was my old base. As long as I divide by it, I can convert to any log of any base log I want. This simply turns to 2.57. We can do the same thing with this one. The original argument was 2, so this is going to be log 2. But we have to divide by the log of the original base, so we're dividing by log 3. This will simplify to 0.63. And it's as simple as that. You just have to remember which things to take the log of to convert your base. Log base 5 of 10, well, that could be written as log of 10 over log of 5. Which is going to become 1.43. Log of 16, or log base 3 of 16 could be written as log of 16 over log of 3. And that's it. Plug it into our calculator and we get 2.52. So converting the base is actually not so bad, and we now have the ability to do it on our graphing calculators. So let's use this new trick to graph a new logarithm. We want to graph log base 4 of x. All right, we don't have a button on our calculator to do it, but we could graph y equals log of x over log of 4. And now we can graph this. So I'm going to switch over to Desmos, and we are going to graph it and take a look at what this function looks like. We then have to find any asymptotes as well as the domain and the range. So log of x over log of 4. Y equals log of x divided by log of 4. This is what our function looks like. It's similar to just log of x, but it's been scaled. Log of 4 is going to be like a stretch applied to the function. All right, so our domain and range. Looks like we can't have an x value that is 0, and that makes sense because you can't have log of 0. Looks like our range, however, is infinite. It doesn't seem like it, but this will go up forever, just really slowly. You can see that it goes down forever. And so effectively, the range is all real numbers while the domain is all x is greater than 0. So if we want to go and sketch this, the function has a shape like this. Oops. The domain is that x is greater than 0. It's not equal to 0. It's just greater than. And then the range is that y is all real numbers. Oh, and we want asymptotes. We have a vertical asymptote at x equals 0. Notice how I tried my best to make it not equal 1. Normally, you'd get an x-intercept of 1 for every log. Since we have stretched by this 1 over log of 4, this value changes, and it's probably actually over here somewhere. I just didn't do the best job of sketching. All right, graphing logarithmic functions by hand. Recall when we graphed log functions by using the fact that c to the x and log base c to the x are inverses. And so we've got this trick. We can make a table of values for 2 to the x, and then we can make another table for log of base 2 to the x. And we just switch the x and y values. This one, 2 to the minus 2 is 1 over 4. 2 to the minus 1 is 1 over 2. 2 to the 0 is 1. 2 to the 1 is 2. And 2 squared is 4. Okay. All we have to do is now switch y and x. What were once our x values became our y values, and our y values become our x values. We can then go and plot it. Where are we here? Minus 2 and 1/4, minus 1 and 1/2, 1 and 0, 2 and 1, and 4 and 2. All right, but this is something that we've technically already done. This is not new. What we're going to do now is we're going to take this function and we're going to apply some transformations. So in its full glory, the log function could be written as y minus k equals c times log base a of d of x minus h. So it looks kind of frightening. However, they're exactly the same rules as before. K is going to be a vertical translation. C is going to be a vertical stretch. D is going to be a horizontal compression. And H is going to be a horizontal translation. The only thing that's different is that our four variables, K, C, D, and H, are in different places than they were before. Anything that's attached to X still is going to either translate it or stretch it. Anything that's attached to Y is still either going to translate it or stretch it. So the only thing we have to remember here is that we need to deal with stretches or reflections first. And then we deal with our translations. All right, so let's try a problem here. We are going to try to graph log base 3 of x plus 5 plus 2. All right, it's going to be based on log base 3 of x, but we're then going to have to apply some transformations. So we're going to use 3 to the power x to create our first table of values. And we're going to just do it point by point because I don't really want to do 3 separate tables. So first points will go minus 1, 0, 1, and 2. 3 to the minus 1 is 1/3. 0, or 3 to the 0 is 1. 3 to the 1 is 3. And 3 to the 2 is 9. Okay. We can now go and switch these x and y values, and now we've got the points for the log function instead of the exponential version. So 1/3, 1, 3, and 9 become x values, while minus 1, 0, 1, and 2 become y values. All right, now here's the tricky part. We have to account for our translations. There's no stretches, or we would have a fourth column, but we have a translation of 5 units to the left. We also have a translation of 2 units up. So effectively, we're going to be subtracting 5 from each of our x values, and we're going to be adding 2 to all of our y values. Let's do one of them at a time. Let's deal with the x values first. 1/3 minus 5 is minus 4 2/3. 1 minus 5 is 4, minus 4. 3 minus 5 is minus 2. And 9 minus 5 is 4. We have to add 2 to our y values as well. So minus 1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. And 2 plus 2 is 4. So if we go to plot this one now, we've got x and y values for each points. Minus 4 2/3 and 1. Minus 4 2. Minus 2 3. And minus 4 4. And so our function takes a shape that looks like this. If you were to take more points, you would find that your vertical asymptote that used to be at 0 has been shifted to minus 5. That's because it's been shifted 5 to the left. So we've actually got a vertical asymptote hidden here. All right, so our domain, x must be greater than minus 5. That's because of our vertical asymptote. The range, y is all real numbers. Our x-intercept is right here. It's going to be, oh, I guess we should solve for that. So our x-intercept is going to be what happens when y equals 0. So if we want to calculate the x-intercept, y equals 0, we'd have the equation 0 equals log base 3 of x plus 5 plus 2. We can move our 2 over. So it's a minus 2 equals log base 3 of x plus 5. We can then write our power. So 3 to the power 2 or minus 2 equals x plus 5, or 3 to the minus 2 minus 5 equals x. So we end up with a y-intercept of minus 4 minus 4.89. So we have an x-intercept of x equals minus 4.89. Our y-intercept is going to be where x equals 0. So our y-intercept, I guess I need a little more room. That's where x equals 0. We can take our equation, log base 3 of 0 plus 5 plus 2. This is simply log base 3 of 5 plus 2. And now we can't put this in our calculator, but we can convert it to log 5 over log 3 plus 2. And this will simplify to y equals 3.46. So solving for our x and y intercepts, we have to do the same thing as we've done in the past. The x-intercept, set y equal to 0 and solve for x. For your y-intercept, set x equals 0 and solve for y. In our asymptote, we have a vertical asymptote at x equals minus 5. All right, so let's do one more of these, and then we'll do some questions where we have to go from the picture back to the graph. This one's going to be more complicated. Unfortunately, we're kind of stuck with it this way. So we've got y equals minus log base 2 of 2x plus 6. We need to actually have a y equals 2 to the x table, so let's do that first. And we will take the points minus 2, minus 1, 0, 1, and 2. And again, I'm going to put them in brackets so I don't have to have a new table for each one of these, but it's the same kind of thing. Left is x, right is y. So 2 to the minus 2 is 1/4. 2 to the minus 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2, and 2 squared is 4. So for log base 2 of x, I just have to switch x and y. I guess I should have included another column here. 1/4 and minus 2, 1/2 and minus 1, 1 and 0, 2 and 1, and 4 and 2. All right, now we can start applying our transformations one by one. I'm going to deal with minus log base 2 of x first. So essentially, I'm taking my reflection and I'm applying that first. It's going to result in multiplying all my y values by minus 1. It's going to reflect over the x-axis. So maybe we'll write that down, reflection over x. And effectively, the only thing that changes is my y values become negatives. So the x's are the same, 1/4, 1/2, 1, 2, and 4. However, the y values will become 2, 1, 0, minus 1, and minus 2. All right, now we have to apply our next transformation, which is going to be another stretch. So y equals minus log base 2 of 2x. This is going to be a horizontal compression by a factor of 1/2. We take the 2 and divide 1 by it. So effectively what we're doing is we're dividing our x values by 2. We're just cutting them in half. The y values will stay the same though. So let's just copy those out. There's still 2, 1, 0, minus 1, and minus 2. All right, so for our x values, we cut them in half. 1/4 becomes 1/8. 1/2 becomes 1/4. 1 becomes 1/2. 2 becomes 1, and 4 becomes 2. Okay, so we've dealt with our not our transformations. We've dealt with our stretches and reflections. Now we have to deal with our translation. All right, now I'm going to rewrite this in a different way because it's very tempting to immediately think that your translation is going to be 6 units to the left. However, we can rewrite this as minus log base 2 of 2 times x plus 3. And I think it becomes more clear written this way that it's actually 3 left, not 6 left. So the last transformation we're going to do, minus log base 2 of 2 times x minus 3, or plus 3. That's going to be a translation 3 units to the left. Or in other words, take your x values and subtract 3. So we're almost done. I know there's a lot of brackets here. The y values stay the same. So it's still 2, 1, 0, minus 1, and minus 2. But our x values, we've got to now go and subtract 3 from them. So 1/8 minus 3 is minus 2 and 7/8. 1/4 minus 3 is minus 2 and 3/4. 1/2 minus 3 is minus 2 1/2. 1 minus 3 is minus 2, and 2 minus 3 is minus 1. These are the set of values that we have to now go and plot. This is our final column. This is the one that actually matters, but it took us a long time to get there because we actually had to plug in some numbers. And now you could just go straight to this column and you could just go, I don't know, minus 3, minus 2, minus 1, 0, 1, and 2, plot those, and then connect the dots. That will get you a fairly accurate graph. However, you have to have a way of calculating log base 2 in the first place. So we can finally plot our points. First point is minus 2 7/8 and 2. Next point is minus 2 3/4 and 1. And then minus 2 1/2 and 0. Minus 2 and minus 1. And minus 1 and minus 2. All right, so as far as our domain, range, x and y intercepts go, let's fill in the easier ones first. Our domain, I think it's fairly clear that we've got a vertical asymptote here. We're getting closer and closer to minus 3. So x must be greater than minus 3. Our range is that y is all real numbers because we can go anywhere up or down. Our x-intercept, we actually have it already. It's minus 2 1/2. Otherwise, we would have to set y equal to 0 and solve for it. The y-intercept we don't have, so we'll have to calculate that. But let's do the asymptote first. X equals -3. So to find our y-intercept, that's where we set x equal to 0. We are going to replace x in our equation with 0. So the function was y equals minus log base 2 of 2x plus 6. I believe this was it. Yep. All right, so we're going to set x equal to 0. So y is going to equal minus log base 2 of 2 times 0 plus 6. Y equals minus log base 2 of 6 And now we're stuck here because we can't calculate this, but we could write this as y equals minus times log of 6 over log of 2. That we can put in our calculators. Is equal minus 2.58. That's our y-intercept. And it's not 1 because we've gone through a transformation. Or actually, sorry, our x-intercept would normally be 1 for a log function. Okay, so last couple of questions we're going to do are kind of the reverse order of what we just did. So we went from having an equation of a function to graphing. Now we're going to go from the graphs of the function and we're going to compare those to the equations, okay? We're going to make the functions. So there's a blue one and a red one, and the blue one is labeled for you to give you kind of a bit of a starting point, okay? So our blue function I know is log base 4 of x. So the red one should be based on log base 4 of x. So let's write this down. It's going to be transformation of y equals log base 4 of x. All right, now let's list our transformations. We have reflected it over the x-axis, it looks like. We have a y or an x-intercept of 1. So that tells me that this function has not been stretched. So there's no stretch horizontally. However, it does look to me like there's a stretch vertically. Originally, our function was 1 away from 0. If we then compare the new function, we're now 3 away from 0. And so what that tells me is that at this specific point, and it's been labeled for us, so we can assume that that is the same point, it tells me that the function has been stretched by a factor of 3, but only vertically because our x-intercept hasn't changed. So there's a vertical stretch by a factor of 3. If we put this all together, we know our function is y equals minus 3 times log base 4 of x. I know there's no translation. I know that it hasn't been stretched horizontally, so x is by itself with no other constants. I know it's got a vertical stretch of 3, and the minus sign accounts for the reflection. So this is the equation for this function. Let's try the same thing with a little bit of a different function this time. Okay. So now, this function looks like it hasn't been stretched because it has the same shape. It's not like one bends faster than the other. But we're going to do some kind of tests here to see how whether or not things have actually been translated, okay? So now, one thing I can tell right away is that my y-intercept, or my x-intercept is not 1, okay? So if my x-intercept's not 1, there's only a couple of things that could have happened. I could have either stretched the function vertically, or I would have gone through a translation up. Now, if I stretch the function vertically, what I would expect to see is I would expect to see it rise in a more steep fashion and then flatten out in a more steep fashion. However, if you put some points in here, let's just compare x values. I'm just going to put them on the corners of each of our squares. Well, these are 2 apart. These are 2 apart, and these are 2 apart. So that tells me that they're kind of bent at the exact same angle. I know it's not a super rigorous way of proving it, but they're not changed. Like this one would suddenly bend faster, and now you'd be 1 apart over here. Because they're exactly the same distance, that tells me that they are not stretched. What I do think, though, is that I think this reg function has been shifted. And the reason why is because what used to be an x-intercept is now at the line y equals 2. So when I see this, what I interpret this as is it's based on log base 2 of x. It has not been vertically stretched, no vertical stretch. I don't believe there's a horizontal stretch either. But what I do see is I do see my function has been translated 2 spaces up. Vertical translation 2. So what that means is I can make my function y equals log base 2 of x plus 2. Or if you prefer, you can join the 2 with your y variable, y minus 2 equals log base 2 of x. And there you go. So this is going to seem like quite a lot of new info, but it's actually not. The only information that's new is the converting between bases of the logarithms. We have done all of this stuff before, just not with log functions. So I've got some questions for you to try. Page 451, 3 to 6, 7, 8, 9, 11. A multiple choice, those ones are going to be bonus. You don't have to do them, but they're going to be extra questions to help. So all I really want to see is 451, 3 to 6, up to 11. I'm going to end this now. So hope everybody has a good rest of the day. I will see you all tomorrow in our chat. And just let me know if you've got any questions or if this stuff isn't fully making sense. Anyways, bye for now.